Okay, thanks for the intro. Yeah, so I'll tell you how to do Makespan minimization using posted prices. This is joint work with Michal, Feldman, and Amos, Fiat. Okay, so I would like to begin by telling you about our model, which is in the online framework. In this setting, we're interested in studying algorithms that do not get to see the entire input in advance. Okay, they only get to see it piece by piece. So in particular, we imagine events arriving on the fly, and these events are fed into an online algorithm. Now, the online algorithm has a bunch of outcomes it can choose from, and it must process the event and decide on a particular outcome. The decision is irrevocable, and moreover, it's based on two pieces of information. It's based on the events that have arrived in the past, and also importantly, it's based on the information provided by the current event that has just arrived. How do we measure the performance of an online algorithm? We study the competitive ratio. We say an algorithm is C-competitive if the worst case ratio over all inputs of the algorithm's cost to the optimal solution is bounded by some value C. Okay? And we're interested in minimizing C. And moreover, we compete against an optimal solution that knows the future. Okay? So it's a powerful thing to compete against. Very strong. In our work, we study online mechanisms that take the form of pricing schemes. Okay, so in particular, we still have a bunch of outcomes to choose from. But now we have a pricing scheme that sets prices over the outcomes. Okay, and very importantly, these prices are set before the event arrives. They're set independently of the next event to arrive. Okay? Then once these prices have been set, an event arrives, and now we interpret events as agents, selfish agents. And these selfish agents experience costs over the outcomes. Okay? In general, their cost consists of two pieces: the price, determined by the pricing scheme, and also a specific outcome cost. Okay? In general, this outcome cost is problem dependent. The outcome costs are shown in blue. And the agent's cost is the sum of these two. Now, since the agents are selfish, they choose an outcome of minimum cost to them. Okay? If there are multiple outcomes of the same minimum cost, the agent is free to choose its heart's desire as long as it's one of the minimum ones. Okay, then the process repeats. After the agent has chosen, the pricing scheme can then set a new set of prices over the outcomes. A new agent arrives, same story, maybe different cost profile, but again, it experiences costs on various outcomes, it chooses the minimum one, etc. We study two types of pricing schemes. One is dynamic pricing and the other is static pricing. In the dynamic pricing setting, the pricing scheme, it's what I just told you about. Basically, the pricing scheme is allowed to change prices over time so that different agents see different vectors of prices. For static pricing, the pricing scheme, we limit it to just setting a single price on a machine, and this cannot change. So every agent sees the same price on a particular machine. Okay? Moreover, these pricing schemes are truthful and arguably simple. Okay? They're truthful because the prices are determined before the agent arrives. So the agent can try to misreport, but it would just be wasting its breath. Okay? And it's arguably simple. It's pretty clear to the agents that they can't really do anything and gain by doing it. They can't really gain. It's clear. Okay, so what do we study? The problem we study in this framework is Makespan minimization. It's a classic problem. Here we have m machines, which represent outcomes, and each machine has some load. And we also have n jobs that arrive in an online manner, and we interpret the jobs, the jobs are viewed as agents, and each job j has some processing time pij on machine I. Okay, and the objective is to minimize the make span, which is the maximum load over all machines. Okay, shown here, the height of this horizontal bar. We would like to make this as small as possible. I just want to stress that, so now we're placing prices over machines, and these prices are not used to make money off of the agents. They're used to help align the local incentives of players with the global objective of Makespan. So we hope to achieve good Makespan with these prices. We study several types of machine models. In the unrelated machine setting, the processing times are arbitrary. Okay? They can have arbitrary shapes over the machines. A less general model is the related machine setting. Here, machines have speeds. And throughout this talk, I assume machines are sorted in increasing order of their speed. And the processing times take a special structure. Okay? It's not completely arbitrary. Each job has some size now, pj, and a job's processing time is the ratio of its size to the speed of the machine. So if you have two machines and one is twice as fast as the other, the job takes half the time to complete. And lastly, the simplest model we consider is the identical machine setting. This is the same as the related machine setting if all machine speeds are equal. Okay? All right. How do we model agent costs in this problem? Of course, agents still pay a price determined by the pricing scheme. And we define the outcome cost to be the sum of the load on machine I plus the processing time of the job on that machine. Okay? The sum of these two quantities represents how long the job J takes, how long it takes to complete processing the job on that machine. Okay? And again, as a reminder, the jobs choose some machine that minimizes their cost. Okay, so I'd like to tell you about our results. Our main results are a constant competitive dynamic pricing scheme for the related machine setting. And we also show an omega m lower bound, m is number of machines, for dynamic pricing on unrelated machines. Okay? For completeness, I'd like to show you the competitive ratio landscape for the rest of these models. So here's the story. Dynamic pricing and static pricing both get constant for identical machines. Dynamic pricing gets constant for related, and static pricing gets log m. And they're both m for unrelated. Okay? Of course, we expect static pricing to be worse. It cannot have a better competitive ratio because it's a weaker, it has less power. Okay, how do these compare to the online world? Well, in the online world, you can get constant for identical and related, and you can be log m competitive in the unrelated machine setting. Okay? So in particular, there's a separation result between dynamic pricing schemes and online algorithms. Okay? Dynamic pricing cannot do better than m, whereas you can get log m in the online world. Okay? By the way, these are all tight. These are upper and lower bounds here. And I also showed you the greedy, how greedy does. And the reason is, if you look carefully at the greedy column and the static pricing column, they're the same. And this is not a coincidence, because another thing we show is that static pricing schemes have the same power as greedy algorithms. Okay? Positive results. It can implement greedy algorithms, and lower bounds for greedy translate to lower bounds for static pricing schemes. Okay, so in this talk, I'm going to focus on our positive constant competitive result for related machines. I'll show you a dynamic pricing scheme in this setting. Okay, what's the main plan of attack? We're going to take an existing online algorithm, which is good. It's constant competitive. And then we're going to massage this algorithm a bit. We're going to design a more flexible algorithm. What do I mean by flexible? I mean the algorithm is allowed to take several permissible actions. Okay? For example, maybe the algorithm is allowed to assign a job j to one of several machines as opposed to just one. And even though we allow this extra freedom, we can show that it's still constant competitive. Okay? And finally, based on this flexible algorithm, we design a dynamic pricing scheme, and we show that it exactly mimics the flexible algorithm. And because it precisely mimics it, it means that the competitive ratio of our dynamic pricing scheme is the same as the competitive ratio of the flexible algorithm, which we show to be constant. Okay, so it would be good for us to understand what dynamic pricing schemes can and cannot do. One very important observation is that agents have linear cost functions. Okay? The y-intercept of this line is the load of the machine plus the price, and the slope of the line is the inverse is the inverse of the machine speed. Okay. All right. So let's see how things behave when you have two machines. When you have two machines, we have two lines, and the blue line with the steeper slope is a slower machine, and the green line with the shallower slope is a faster machine. Okay? So this point of intersection, where these two lines intersect, is an interesting point, because before this point, before point A, job J prefers machine 1. After this point, job J prefers machine 2. Okay? So what can pricing schemes do? Suppose we try to increase the price on machine 2. What we do is we lift the green line, and therefore we change the point of intersection to a later point. Okay? It now intersects the line at point B. What this means is that job J now prefers machine 1 for a longer interval. Okay? Because machine 1 is now more attractive. And then again, past point B, it prefers machine 2. Note that if we increase or decrease both prices at the same rate, we do not change the intersection point. All we do is just change the absolute costs. Okay? So for example, you could assume that the price on machine 1 is, without loss of generality, 0, because you could just decrease both prices until it hits 0. Okay, let's understand some of the limits. First of all, in this model, agents prefer faster machines as their job size increases. Okay, the reason for this is if you're on the minimum line and you travel along it, the only other line you can hit is a line of shallower slope, which means you're hitting a machine that's faster. Okay? This means that if we're trying to mimic an online algorithm, it must have this form. Another issue is tie breaking. At this point of intersection, job J is indifferent between the two machines. Okay? Whereas an online algorithm might say, no, you have to go to machine 1, but the job may choose machine 2. Okay? So I'm not going to say much about this. All I will say is this is one reason why we need the algorithm to be flexible. If we want to mimic the algorithm, we really must allow it to assign job J either to machine 1 or machine 2. We must be OK with both options. OK, so let's see how to mimic an online algorithm if it satisfies this nice form for two machines. Suppose when job J is small, it goes to machine 1, and when job J is big, it goes to machine 2. What can you do? The price on machine 1 is 0 without loss of generality. All you do is you set the price on machine 2 so that the intersection point is precisely at A. And now you've mimicked this online algorithm if it satisfies this form. There's one issue, which is that if machines have the same speed, you cannot force this crossover point to happen, but we ignore this for now. OK, how about 3 machines? I claim we can use what we just learned for 2 machines to build up to 3 machines and more. How do you do it? So pretend machine 3 does not exist. Set the price on machine 2 so that the intersection point is at A. And now consider another world where machine 1 does not exist. Place a price on machine 3 so that the intersection point is at B. And now we'd like to merge these two worlds. How do you merge them? Just lift both lines at the bottom so that they match up. Just increase the price by pi 2j. And now you have the property that job J prefers machine 1 on the left, and machine 2 in the middle, and machine 3 on the right, which is precisely what we wanted. Okay, so the online algorithm that we're going to mimic is called slow fit. It was shown to be 8 competitive. I'm going to assume we know the value of opt. Slow fit is the following. Whenever a job J arrives, it computes this set S, which represents the set of machines on which running J on is feasible. Okay? Where placing the job on the machine does not cause it to be much larger than opt. And then it chooses the lowest index machine in S to assign the job to. Okay, so I claim that this algorithm satisfies the nice form that we need. Yeah, okay, and it's proven that this set is never empty if the estimate is at least opt. Okay, this is important. Okay, so let's consider what it means for a machine to be feasible. If we rearrange terms, we see that a machine is feasible if and only if the job size is smaller than this quantity, SI times 2 lambda minus the load. Why is this useful? Because if the job size is to the left of this point, the machine is feasible. If it's to the right, it's infeasible. Okay, and since the algorithm is correct, if the estimate is at least opt, there always is a feasible machine. Okay, so let's see how to look at the assignment profile for this algorithm. Let's understand which machines it assigns job J to as a function of the job size. So here I've computed these crossover points, UI, and let's sort them in increasing order. And let's try to understand which machine job J gets assigned to. At the leftmost point, all machines are feasible. So slow fit will assign job J to machine 1 in this case, because that's the lowest index. How about the next interval? It's a similar story, except that machine 1 is no longer feasible, so now it will assign job J to machine 2. Same thing in the next interval, same thing in the next interval. Now, machine 2 is no longer feasible after this point. Machine 4 becomes the next lowest index that's feasible. So in that region, we will assign to machine 4. Note that jobs cannot have size past this point because the set S is never empty, so there always exists a feasible machine. So what do we do for prices? Well, slow fit never assigns the machines 3, 5, and 6, so we set a price of infinity on them, forget about them. And for the rest, we see that it satisfies this nice structure. When the job size is small, we assign to machine 1. When it's medium size, we assign to machine 2. And when it's large, we assign to machine 4. But we already know how to mimic this online algorithm. We discussed it earlier regarding pricing schemes. Okay? So that's all I wanted to say. So in conclusion, our main results are a constant competitive dynamic pricing scheme for related machines. And we also show an omega m lower bound for dynamic pricing on unrelated machines. And we also show that the greedy algorithm has the same level of power as static pricing schemes. Some avenues for future work. Currently, prices can be quite different across machines, so it'd be nice to have some kind of control over that. It would be good to better understand online mechanisms versus pricing schemes to better understand what kind of power they have. And finally, it would be good to design more pricing schemes for more online problems. Okay? Thanks.